Hello everyone, and welcome to today's chem lesson. Today, we are going to spend some time talking about the three phases of matter, the transitions that occur between each phase of matter, and how that connects back to energy, whether it is absorbed or released. First, we want to do a quick overview of the phases of matter. I know we've seen these before in other science classes, but just to reiterate and make sure that everyone starts on the same page, we want to talk about the difference between solids, liquids, and gases. Solids have a definite shape and a definite volume. The particles of a solid are fixed in their place, right? They are arranged in rows and columns, right? Nice orderly patterns. And they only vibrate slightly, right? The only movement that occurs in a solid is slight vibration of the particles. They have this orderly geometric pattern. Sometimes they call it a crystal structure, right? This particle diagram here shows a solid. Now, when we go from a solid to a liquid, the particles keep their definite volume, but they lose their definite shape. By taking this nice orderly geometric pattern and breaking it down and giving these particles range of motion, they now lose their shape. There's nothing holding them rigidly in one shape anymore, and they take the shape of their container. They adapt to whatever you pour them into. The particles, like I just said, move freely past each other, right? They can move in front of or behind or on top of, right? They have free range of motion around each other, and they have no pattern or arrangement. When we go one step further and become a gas, we keep this moving freely around, we keep this no regular pattern, but we now lose the definite volume. These particles have been expanded, right, spread apart from each other so much, and sped up so much, they're moving so fast, that they expand to fill the entire container. They can be compressed down into a small container or let to grow into a big container, right? But they fill whatever container you put them in entirely, from wall to wall, and the particles move in straight lines until they collide with another particle or a wall. Now, if we as scientists want to talk about water, we can talk about solid water or ice, we can talk about liquid water, or we can talk about gaseous water. But each one of those things has the same chemical formula. They're all H2O, even though they are different phases of matter. The thing that we use to differentiate between the phases of matter are going to be these little subscripts down here that are going to tell us solid, liquid, or gas. Right? S for solid, straightforward. A script or cursive, L for liquid, and a small lowercase g for gas. Right? S for solid, L for liquid, G for gas. Pretty straightforward. There is a fourth small subscript that we will see, and that is AQ. Right, we might see something like, I don't know, potassium iodide, AQ. This AQ is not a different phase of matter. It is, in fact, aqueous, which means mixed with water. Right, so if we wanted to say salt water, we would say NaCl, AQ. It's so common and so frequent to mix things with water that we have this terminology, this small symbology for it. Now, if I were to ask you which of these samples was arranged in a regular geometric pattern, you would tell me which one. the correct answer here is choice 4. Right? A regular geometric pattern is something that occurs only in solids. It's the only one with a definite shape. Right? Meaning we're looking for whichever one is the solid. The substance, right? It doesn't matter if it's HCl, NaCl, N2, or I2, right? We could put whatever we want here. What we're looking for this answer is subscript S. We're looking for which one is a solid. Now, as we talk about these phase changes, right, and going between solid and liquid and gas, we also want to talk about the energy required to make those changes. And so we want to also introduce or reintroduce a couple of little tidbits about energy. Right, first is the law of conservation of energy. Right, energy cannot be created or destroyed, it only transforms from one form to another. We're never going to get rid of energy. We can take it out of something and put it into something else, but we are never going to get rid of it entirely. We're going to talk about two major forms of energy. We're going to talk about potential energy, which is the energy of position, right? That has to do a lot with what we were talking about before with the particles and how they're arranged, right? That's compositional potential energy or positional potential energy. Right? There's energy stored in particles that are still. There is not as much energy stored in particles that are moving. Later on, we're going to talk about just plain and simple chemical potential energy, which has to do with the bonds in a substance, right? So the Na bonded to the Cl, there's energy in this bond, right? This is what you talk about when you talk about storing energy in terms of photosynthesis, right? Taking energy from the sun and storing it as chemical potential energy. Right? We're going to talk about that at a later date. Right now, we're talking about positional or compositional potential energy, right? How things are arranged and how that energy can be stored or removed. The other half, right? We've got potential energy, which is energy stored. We also have energy of motion. We have kinetic energy. Right? Kinetic energy is entirely due to motion. And believe it or not, when you take the temperature of something, you are actually measuring the kinetic energy of that thing. Right? Temperature is a measure of the average kinetic energy of a substance. Which means something with a high temperature has a high kinetic energy. Something with a low temperature has a low kinetic energy. Right? Temperature and average kinetic energy are the same thing. A few minutes ago, when we were talking about solids, I said that they vibrate in place. Right? They are still moving, just not moving very much. That motion, right, that vibration of a solid stops at absolute zero, at negative 273 degrees Celsius. There is no temperature colder than that. Right? Again, because temperature is a measure of kinetic energy, it's a measure of motion. And so if there is no motion, that is the coldest you can get. Now, scientists at the time that this was discovered or theorized didn't really love negative 273. Right? They didn't like that it went down to negative 273. It seemed arbitrary. And so what they did was they created the Kelvin system, which sets absolute zero to 0 Kelvin and then goes up from there. The really nice thing is that 1 Kelvin is exactly the same size as 1 degree Celsius. And so it's really easy to go from a 1 to the other. You are either going to add 273 or subtract 273, depending on which way you're going. From Celsius to Kelvin, you add 273. From Kelvin to Celsius, you subtract 273. That formula is on the reference table for you. It's actually the very last thing on the very last page. It tells you that to go from Celsius to Kelvin, you add 273, and to go from Kelvin to Celsius, you subtract 273. So now we want to put these ideas together. We want to take the idea of solid, liquid, gas and combine it with the idea of kinetic and potential energy and talk about how we move from one phase of matter to the other and how that affects the energy of those substances. And so we need 2 new vocab words now. We need to talk about endo and exothermic reactions. An endothermic reaction, or an endothermic process, and an exothermic reaction, or an exothermic process. In an endothermic reaction, energy enters the substance. Right? Energy is absorbed by whatever thing you're measuring. Right? You need to put energy in to make an endothermic process happen. For an exothermic reaction, energy exits. Which means whatever substance you're looking at, whatever you're measuring, energy is being either released from it or taken out of it. Right? If you're taking energy away, if you're cooling something down, that is an exothermic process. You have to take energy out of that thing in order for it to change. If you're heating something up, that's an endothermic process, right? You need to put energy in order to make that happen. And so what we're going to do is we're going to look at each phase change and talk about whether or not it is an endo or exothermic process, an endo or an exothermic change. So let's start with changing between a solid and a liquid. If we go from a solid to a liquid, we know what that is. We've done this before. That's melting. That process is going to make the nicely arranged particles of the solid break their hold on each other, right? Loosen up, start to move a little bit more, and gain that freedom of motion to move in front of or behind or around the other particles. When I melt something, is that endo or exothermic? Does energy enter or do I take energy away? This is an endothermic process. I need to put energy in to a solid in order to make it melt. Right, in order to make that transition from a solid to a liquid, I need to put energy in to speed those particles up, to spread those particles apart. But now I've got this liquid, and now I want to make it a gas. So going from a liquid to a gas, that's evaporation or boiling. Right here, I'm spreading the particles apart even more, speeding them up even more, making them expand to fill the container and lose that definite volume. By doing this process, am I putting energy in or taking energy out? Is this an endothermic or exothermic process? This is also an endothermic process. Right? You need to put energy in to change this liquid into a gas. You need to put energy into these particles to make them spread apart, to make them move faster, to make them expand to fill the whole container. Right? You need to put energy in order for that to happen. What if I want to take that gas and make it a liquid again? Right? Going from a gas to a liquid is called condensation. Right, I'm condensing that liquid or that gas back into liquid form. I'm bringing those particles closer together. I'm slowing them down. I'm compressing them into a liquid. They're going to take the shape of whatever container I have created for them. Is that an endo or exothermic process? Am I putting energy in or taking energy out? Here is the opposite of going from a liquid to a gas. Here it is an exothermic process. I need to take energy out of the gas. I need to cool down the gas. Right? We're talking about temperature being the same thing as kinetic energy, so lowering the temperature is lowering the energy, right? Taking the energy out of the gas to make my substance a liquid now. Now, going from a liquid back to a solid, right, one of our last options here, is called freezing. That's the no-brainer, but it's also called fusion. Right, fusion is just a fancier word for freezing, going from a liquid to a solid. Here I'm going to slow these particles down even more, compress them together even more, making them into a nice orderly set of rows and columns, right? A nice crystal structure, a nice geometric pattern for these particles. Is that endo or exothermic? Am I putting energy in or taking energy out? Here it is also exothermic. Right, I need to pull energy out. I need to cool down the liquid. I need to freeze the liquid. Right? Freezing has become synonymous with cold. Right? So freezing it, taking the energy out to make it solid. You'll notice, or maybe you didn't, but I'm going to tell you now, these are opposite processes, right? If we talk about liquid to a solid, that's exothermic. But solid to a liquid, that's endothermic. Right? Each phase change is the opposite of what it was before. Right? All of our liquid to gas, that was endothermic, but gas to liquid is exothermic. It can't be exothermic both ways, and it can't be endothermic both ways. It must be opposite. These aren't all the phase changes, though. We also have we also have certain times where solids go straight to gases, or gases go straight to solids. Right? Skipping liquid altogether. Now, like we just said, these must be opposites. One of these is endothermic, and one of these is exothermic. Which is which? Which one of these is the exothermic process? All right, good call. Right, sublimation is the endothermic process, and gas to solid, right? Deposition is the exothermic process. I need to put energy in to go from solid to gas, and I need to take energy out to go from gas to solid. Right? If we think about what we just said before, solid to liquid is also endothermic, liquid to gas is also endothermic. Gas to liquid is exothermic. Liquid to solid is exothermic. So it makes sense that if we go straight from gas to solid, it's still exothermic. And if we go straight from solid to gas, it's still endothermic. One final question to wrap us up for today. Which one of these changes results in a release of energy? These are small lowercase l's. Which one of these changes results in a release of energy? For something to have a release of energy, we want it to be an exothermic process. The only one of these processes that is exothermic is going to be going from gas to liquid. We have to cool something down in order for it to go from gas to liquid, releasing or taking out that energy. All the rest of these options are endothermic processes. You need to heat up a solid to make it a gas, heat up a solid to make it a liquid, heat up a liquid to make it a gas, but cool down a gas to make it a liquid. And with that, I'm actually going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.